All right, the second half of lesson 36. So we're just looking at that exponential notation. So from first principles, I want to take a look at what is the derivative, okay, or how do we derive the result when we're dealing with an exponential function. So I'm looking at the limit as h approaches 0. So from first principles, f of x plus h minus f of x over h. So that would be the limit as h approaches 0 for b to the exponent x plus h minus b to the exponent h. So remember, our variables are in the exponents now. And when I look at what's common here, I see that, and I keep wanting to, that should be b to the x, right? Sorry. We can common factor out a b to the x, and this is where I stretch your understanding of exponent rules. B to the x is common, because remember, when you multiply exponents together, you add them. So the first term has an x plus a bit more h, so it's really b to the h minus 1. That's all divided by h. All right. If we were to do distributive law, you're adding your exponents, b times b, so you add the exponents, you get the x plus h, and then times 1. So that's why that works the way it does. All right, so here we are. We now have an expression for the limit, and what we notice is that b to the x doesn't cause us any problems, so I'm going to move it out front. So b to the exponent x multiplied by the limit of h approaching 0 for b to the h minus 1 over h. Well, what is that equal to? Well, we don't really have a mathematical approach in terms of being able to calculate this. So when mathematicians are struggling with this, and they do a whole bunch of research and derivations into it, what we realize is that if this expression, if I want to deal with this expression, it would be really nice if I can get this to equal 1. That would be fantastic. So the only way that would work is to find a value of b that works that way. So we need to find a value of b to make it work. And that's what we're going to do. So I'm just going to pull up Quattro Pro here for a second, so if you bear with me. And see how quick that was? I just pulled that right up. So here's a spreadsheet, and on the top, so you can see that I've got the equation entered in. So the calculations are shown here. So what I'm going to do is I'm going to copy and paste each column for you. So I try base of 2, a base of 3, a base of 2.5. And the reason I pick those bases, so if I copy and paste, we find that with a base of 2, the closest we can get to 0.71. So then I move to a base of 3, and you can see that a base of 3, I want to get closer to 1, so it starts off above. So I hit paste, and you see that I never get close enough. So in the previous one, it didn't get large enough, and now with using base of 3, it doesn't get close enough to 1. So I picked a number in the middle, picked 2.5, and this is basically how they came up with this particular process. So if I paste that value in, you can see again, I get very, very close. So it's got to be a number bigger than 2.5. And I can continue doing this for a while, but rather than drag it out, go back to the smartboard file here. What we find is that if b is equal to 2.71, 828, etc., so dot, 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 the property slash limit as h approaches 0 for b to the h minus 1 over h will in fact equal 1. And rather than writing that number out, what mathematicians have said is let E equal 2.71828, so on and so forth. And you'll find that button on your calculator. And what we call this the natural base. Natural base. So base e is what we call the natural base. So finishing this up, what can we draw from our conclusions here? Our natural base is e 2.71828, so on and so forth. If we use our natural base in a logarithm, so I'm talking about right here, it's written as y equals ln x. So those two are equivalent. So if you have a base e, we call it a ln now, ln, where ln is what we call the natural logarithm. And finally, where I'm ending the lesson today, and there's no homework associated with today's lesson, if I follow through and if we let b equal the natural base, then we take our limit as h approaches 0 for f of x plus h minus f of x over h. So it's the limit as h approaches 0 for b, now it's e to the x plus h minus e to the x over h. We can common factor out, so the limit as h approaches 0, e to the x, bracket e to the h minus 1 over h. We know that from this property, that goes to 1, so it's e to the x. So therefore, if y equals e to the x, the derivative is e to the x. So the natural logarithm has a really neat identity where the derivative of it is just itself. We're going to talk about some of the applications and how it ties into our derivative rules in the next lesson.